thank you everyone for coming to today's session. Before we delve into our discussion, let me first give a very brief introduction about myself. I am Ilana Makover, and I am a machine learning engineer at Bluevine. Now, let's get back to the real reason everyone's here, which is let your data tell its story. Let's talk about a fictional streaming service. Let's call this service Flix. Every time you hit that play button, Flix quietly collects information. It tracks things like how long you watched, whether you paused, skipped ahead. One data point they store, let's say it's called average watch duration. That one data point behind the scenes has a whole story. When you press Flix's play button, an event is sent by the playback service. That event is then collected into the streaming logs. Then a daily analytics job reads that event to calculate the user's average watch time. Then the recommendation model reads this data point, average watch duration, in addition to others, to determine what TV shows and movies to suggest to you tomorrow. Next, the marketing team reads this data point, average watch duration, in addition to others, to decide which email you get in the next email campaign. And finally, the BI dashboard reads this data point, average watch duration, aggregates over all users, and then shows executive engagement trends. This one data point, average watch duration, quietly flows through many different systems, powering recommendations, marketing, business decisions. Oftentimes, people look at data at face value. They check things like the data type, data integrity, trends in the data, but many forget to zoom out and look at the bigger picture. Let's go back to our Flix example. Let's say Flix changed its data point of average watch duration from seconds to minutes. Would you know the downstream impact of such a change? Would you know which teams have to be involved in such a change? Which models have to be retrained? Dashboards need to be updated? And let's say Flix's recommendation engine starts acting weird suddenly. Would you be able to identify upstream causes of such behavior and trace it back to this updated data point? And finally, this is an aspect some of us overlook. Is this data even used? Perhaps Flix is still getting data from an external provider, yet no one is using it. Perhaps Flix is generating data for a research project that ended ages ago. Now, there is data floating around, taking up space, taking money. This is where data lineage enters the picture. Data lineage allows us to understand and even visualize this network of dependencies and allows us to quickly answer these questions in front of you. Data lineage is a story of listening to your data as it jumps across your data pipeline, listening to things like where it came from, how it moved, how it was used. These stories allow us to see the data's true value. Today, we'll explore how to listen to that story. And together, we'll build a lightweight data lineage solution. Our agenda for today will be as follows. We will first discuss what we want to listen to. This will answer three major questions: what data, which data interactions, and what details. Then we will go into our data lineage solution step by step, which of course answers the above questions. And finally, we'll top it off with a great visualization. The first step when we want to plan our data lineage solution is to think about what data you'd like to track. For better or for worse, not all data is created equal. Some data might be more useful to your organization than others. Data can be obtained by an external provider, and it can be generated in-house, right? Flix may want to know some information about their users. They could buy this information from an external provider, and other information they can generate in-house. Do you want to track data obtained by an external provider? Data generated in-house? Data can be stored across multiple databases and data warehouses. Do you want to track data from specific databases? Data from specific data warehouses? Some of them? All of them? For our example purposes, we will say we want to track all of our processes that read/write our in-house generated data that is stored in our tabular DB and our graph. Amazing. Now we get on to our next section, which data interactions. We will now start exploring data interactions in our system. Most data journeys are composed of many interactions, whether it be reading from a database, dumping a file on some cloud storage, interacting with a model. To understand the data journey, we will need to identify our interactions between agents in our system and the data itself. You could say these data pipeline interactions help shape the data's character, like in a story. Let's walk back to our original example, which includes a recommendation model. This model makes a decision on what TV shows and movies to recommend to you based on inputted data. This interaction between data and model is something we want to track. This is vital. In addition to tracking this specific interaction between this data and this specific model, we also want to track other interactions between our data and all of our models. So we want to find the common entry point where this data interaction happens, where all of our data and our models interact in this one common area. And here, our engineering best practices come into play. We will be under the assumption that your team created some generic API to handle model inference that is model agnostic. Amazing. And this generic API, right, it could be some models call some of the methods here, other models call other methods, but at the end of the day, based on our engineering best practices, all models will begin their model inference journey in a common entry point. And for our purposes, let's say it all begins, all the models, their common entry point is in this predict method. This predict method is where we want to locate our data interaction for data models. Now we have located one such example of a data interaction. Now we simply have to locate all the other major data interactions for your APIs, microservices, and internal tools, which leverage your data. This is the key. This will make implementing your solution much easier. Once you leverage these central entry points, you can then record valuable information about your data and its current location in its journey. Once you localize this part, the storytelling bit will seamlessly fall into place. One final aspect we need to discuss is categorization. Every data interaction will be categorized in a very simplistic manner. Either it is a read interaction or it is a write interaction. Either it is consuming data, it is reading data, or it is writing data, it is generating data. Now, let's tie our section together here with a clean example, and this example will follow us through today's session. So let's say we have a central method called readTabularDB, and our group uses this method in order to query from our tabular database. This is our central entry point. We have now localized this. Now we want to categorize it as a read interaction because it is consuming data. It is reading data. Again, this method is used to query to our tabular databases. The hardest part of all this will be deciding what information is critical to understanding your data. Every story needs a good genesis. What is your data's hero's journey? We will go over some possible examples now, but keep in mind, you will have to answer the overarching question of what information will be useful to understand your data. Again, some examples. What process is requesting this data? If we go back to our example, we'll say recommendation engine is requesting this data. When did this request occur? November 4th, 2025. Which main entry point was called? Read tabular DB method. What data was requested? We can say 2 columns were requested, average watch duration and average time paused. What is the source of the data? We can say a table called ag user watching metrics. What is the source type of the data? It is a database. And finally, what type of interaction is this? This is a read interaction. Now, before we dig into the implementation aspect, let's take a little step back and discuss our functional requirements of our data lineage solution. Data lineage should trace, visualize, and understand the journey of data across our systems from the moment that data is consumed through its transformations to its ultimate points of use. We have 5 functional requirements. The first one, we want to list every possible downstream process, model, system that uses a data point. Next, we want to identify exactly where a data point starts. Who creates this data point? Which process, model, system creates this data point? Next, we want to visualize the full data journey. This will help us both understand possible downstream impact of data failure or data change, and also identify upstream causes of odd behavior. Put simply, we want to understand also, is a data point even used? And if it's not used, let's eliminate it. And let's improve efficiency. And finally, our last functional requirement, we want lineage to be automatically collected and updated as our jobs evolve, as our systems evolve. So we want to have the latest view of our pipelines. Now, we get to our high-level solution. Now we can focus on listening to our data as it moves across our pipeline. In front of you is the lightweight, in-house data lineage solution. Our solution will require 2 things, one of which is a queuing system of your choice and a table. The queuing system will have to have a mechanism to ensure that no 2 identical messages can be queued. So to break this down even further, let's say a message is in the queue, an identical message cannot be enqueued at this point, and the table will store all of our data interactions. Now let's go step by step into our solution. Once the information details are agreed upon and finalized, the main entry points, which we identified earlier, each main entry point will have to obtain the relevant data details. And they will get these data details, package it as one message, and send it to a queue. Let's dig a little deeper. We mentioned an entry point earlier called read tabular DB. As mentioned, all of our queries to our tabular database, they all enter this location. And let's say our recommendation engine calls this entry point 3 different times for 3 different queries. Let's follow the light green here. We can see 3 different times for 3 different queries. That means we see 3 different messages in the raw interactions part. So now we have 3 different messages. Let's break this down even further. Let's talk about a very specific example. Let's say our read tabular DB gets this query as input. This query is very straightforward, very simple. We can see select 2 columns. One is called average watch duration, average time paused, from ag user watching metrics. Read tabular DB entry point has to get this query, parse it, extract the relevant information in order to write something like this, to extract this message from that data interaction. And we see here, again, this is all happening in read tabular DB. It takes this one query, it extracts the relevant data details, it extracts that the process that called this entry point is called recommendation engine. It extracts the request time, which is November 4th, 2025. It extracts 2 columns were called. One is called average watch duration. One is called average time paused. It also extracts that the table that was requested, the source is called ag user watching metrics. etc., etc. This is an example of one process, of one entry point that has to obtain this information and send it as a message to a queue. This is all happening at the same time that the existing process is happening. So read tabular DB and all other main entry points have to extract this information and send it as a message to a queue very quickly, because once this happens, it needs to continue on with its regular scheduled programming. Now, this one message here can be a bit sloppy and not so easy to read. We will call it the data's first draft of storytelling, right? It looks clean to you now, but imagine the query were slightly different in our case. Imagine we were querying 20 columns. Then the message would look very sloppy, right? So now we have a very sloppy message, a lot of information, and now we get on to our next part of the process. Now we have a new independent process. This process, what it does, it dequeues from that queue, which has all of our messages, which talk about many data interactions. And this process takes a message and splits it into more bite-sized pieces, where each piece talks about exactly one data point, right? So why do we do this? Because when you want to tell a story, you want to talk clearly and concisely. Let's go back to our example. At this stage, our example of one message, by the time it gets to this independent process, it gets split into two different messages. If we look at the top part of the screen, this message is more or less the same message that we have seen earlier. The only difference is what is marked in red is that now it talks about exactly one data point. Now we only talk about column average watch duration in the message, and then if we look at the bottom message, we only talk about average time paused. So again, this part of the process, it simply takes a message, breaks it down into multiple messages, where each message talks about exactly one data point. Both these messages are now sent to a new queue. Now we get to one of the last parts of the architecture. Now we get to populate data lineage table. This new independent process will dequeue messages from that second queue, and it'll update and insert these messages into a table. This is how it will look like. Those two messages that we have seen in the previous step will be 2 rows now in our data lineage table. Amazing. We can see here, we have in our table the process, which is called recommendation engine. The entry point is called read tabular DB. The data point is average time paused. The source is ag user watching metrics. Amazing. Again, this is done in update and insert format when we interact with the table. This is an example of just that one message that we saw turned into 2 messages and now into 2 rows. But imagine all of our data interactions for all of our processes are in the table. Now we'll have much more information. And with this information, at the moment, we can do so much with this when it's just in the table format. I will go over a handful of examples of what we can already do in this table, but of course, there's way more that one can do with this table. So, what's an example? Let's say we want to understand what the process called recommendation engine, what is it dependent on? So from that table, we can see, right, in order for our recommendation engine process to run, it needs to read 4 different data points. If it needs to read 4 different data points, we will say it is dependent on this data, right? So from the table, we have blotted out only the dependencies of recommendation engine, and we're going to call this the first level of dependencies, right? It's like the nuclear family. And then, let's say we want to dig a little deeper. What about that second layer of dependency, that second level of dependency? So, right, recommendation engine, it reads from 4 data points, but maybe we want to know who writes to those 4 data points. We can look at our table and we can clearly answer that question. The 4 rows on the top, those are who writes to those data points. that is then read from recommendation engine. As we can clearly see here, for example, recommendation engine reads data points average watch duration, average time paused, and watch duration. So that's that one level. And that second level, who writes those data points? Well, we see playback service writes data point watch duration and time paused, while data aggregator writes the other two, average watch duration and average time paused. Watch duration, time paused, So this is that second level of dependency. There's way more that we can do by just looking at this table, so much more to extrapolate, but now we will get to our storytelling bit. Now, all of our sentences are in our table. Each line is a sentence in our story. And now we just have to string together our sentences in order to tell our story. And like all stories, we need to begin ours at the beginning. So how do we write our story from the beginning? We will need to utilize a helper method. This helper method utilizes recursion. We can talk in private after about more details, but because our time is short, I will just simply give the gist of what this helper method does. So this helper method, the bottom line is that it takes a data point and it returns the whole journey of that data point, and you can give the journey for however many levels of dependency you want. So let's go a little step by step into this helper method. This helper method, it takes in one data point, it queries the table, and it checks which process writes to this data point. Amazing. We take all those processes, we add it to the stack. Then we want to see, what does this process depend on, right? Who does it read from? What are the data interactions that it reads from? So at this point, for each process, we now retrieve each data interaction that is read from, that is dependent on this process. Then we add all of those to our stack. Then we essentially pop it from the stack. But at this point, bullet points 1 to 4 talk about exactly one level of dependency. Once we pop from the stack and continue on this cycle, then we get to that next level of dependency, and you can go on and on for however many levels of dependency you would like to see. Amazing. Now we can read our story from start to finish. Now we just have to use a Python package, which we call PyViz, and let's package everything together. Let's tell a very small story of our data point, average watch duration. Let's just paint the story if this data point is even in use. So again, leveraging our table, leveraging our helper method, and leveraging PyViz, we can now see a very small story, a snippet story of this data point. And we can clearly see on the left-hand side, this process called daily user metrics writes this data point. And on the right-hand side, we see two different processes that utilize this data point, that use this data point. Amazing. So now we know, yes, this data point is in use. We don't have to delete it just yet. Now, let's paint another picture. Let's paint the picture of daily user metrics. We want to know what happens during this process. So again, leveraging our table and our helper method and our visualization, we can also paint this picture here and this story of daily user metrics. We can see not only does it write this data point, it also does some other things. It reads from two other data sources. It reads from the graph, it reads zip code for some reason, and from Iceberg, it reads total watch time. Now let's paint a fuller picture of our process and our data point. And what do we get here? We get a fuller picture of what happens in our data pipeline for average watch duration. For our purposes, this is a very slim and trim picture of our data point. Of course, we can go on and on because there will be many levels of dependency in your processes, but this is a very slim and trim picture. And if we go back to our functional requirements of what data lineage comes to solve, we can clearly see here, if average watch duration was updated from seconds to minutes, we can clearly see the downstream impact or the possible downstream impact of such a change. We can clearly see here that recommendation engine and BI engagement trends might be impacted, and we should focus our time on those processes. And on the flip side, another thing we can see from this lovely picture, which also answers our functional requirement, if we start noticing that recommendation engine starts acting weirdly, we can clearly identify upstream causes of odd behavior, and we can see that, oh, it's dependent on average watch duration and this model, and then we can localize our debug time. There's so much more we could extrapolate with our time here. I just want to answer one of the other functional requirements, because at this point, you guys may be asking, but what about knowing if a data is even in use? How will that look like? Well, I will answer that question with a visualization. We will see if a data is orphaned, which means that data is not in use, we would just see that a process is writing to that data point, but we won't see any other process leveraging that data point. It'll just be orphaned. And this is a data point, average num skips. Maybe we could remove it from our table. There are some key takeaways that I hope everyone takes from our time together. You can listen to your data, and you can listen to its journey. By having the latest view of your data pipeline and your data systems, you can easily cut back on debug time and simply focus on the downstream impact of a data failure or a data change, and you easily know where to focus your time and energy. And also, you can cut back debug time when you're trying to identify upstream causes of odd behavior. And of course, these days, we also love removing waste and improving efficiency. So through data lineage, we can also maybe not utilize a specific external provider because we clearly see that it is not in use. Thank you for your time.